Proof of exhaustion. The proposition of the form for every x belongs to S p of x is true if p of x is true for every x in S. If S consists of only a limited number of elements, we can prove that the statement for every x belongs to S p of x is true by considering p of a for each a in S, verifying that p of a is true. Such a method of proof is called method of exhaustion. This method works only when S has limited number of elements, and verification of the truthness of P of A for each A belongs to S is not hard. Proof that every even integer n with 2 less than or equal to n less than or equal to 26 can be written as the sum of at most 3 perfect square. Let us consider the even integers s, that is 2, 4, 6, 8 and all. So the given statement is for every x belongs to S, p of x is true where p of x given as x is the sum of at most 3 perfect squares. 2 equals to 1 square plus 1 square, 4 equals to 2 square, 6 equals to 2 square plus 1 square plus 1 square. Again for 8, 2 square, 2 square, 3 square plus 1 square. Then 2 square plus 2 square plus 2 square will give you 12. For each x in S as the sum of at most 3 perfect square is given till the number 26. Then the proof of existence. The proposition of the form there exists x belongs to x, p of x is true if any one element a belongs to S such that p of a is true is exhibited. Hence, the best way of proving a proposition of this form is there exists x belongs to S, p of x is to exhibit the existence of one a belongs to S such that p of a is true. This method of proof is called the proof of existence. Prove that there exist positive integers m and n such that m, n and m plus n are all perfect squares. Positive integers, yes. Let m be the 9 and n be 16, which both perfect squares. M plus n, 9 plus 16 is 25. 5 square is also a perfect square, hence the proof. Hence that there exists a real number x such that x cube plus 2x square minus 5x minus 6 is 0. Let x equals to minus 1. Then we will have minus 1 cube minus 1 plus 2 minus into minus 1 is 5 minus 6, 5 minus 6, that is plus 5, 5 plus 2 is 7, minus 6 is 1, and here minus 1 plus 1 get cancelled, then it is equal to 0, hence the proof. Then disproof by contradiction. To disprove a conditional if P then Q hypothesis, P is true and Q is true. Disproving this, let us consider both are true. End up with the contradiction. In view of contradiction, we conclude that the conditional if P then Q is false, but this method is of disproving if P then Q is called disproof of contradiction. Disprove the statement. The sum of two odd integers is an odd integer. The proposition to disprove the sum of two odd integers is an odd integer is considering both as true if P then Q. The sum of two odd integers a and b are odd integers. Then a plus b is an odd integer. Hypothesis, let us consider P is true and Q is true. A equals to 2k1 plus 1, B equals to 2k2 plus 1, then A plus B is 2k3 plus 1 for all k1, k2, k3 belongs to integers. So A plus B is an odd integer. A plus B, considering this as 2 of k1 plus k2 plus 1, we will have, which shows that AB is even, which is a contradiction. So the given statement is false. Then disproof by counterexample. The proposition of the form for every x belongs to S of P of x. Counterexample is false if any one element of A belongs to S such that P of A is false is executed. Hence, the best way of disproving a proposition involving a universal qualifier is to exhibit just one case where the proposition is false. This method of disproof is called disproof by counterexample. The particular case where the proposition is false is called the counterexample. Disprove the proposition that is the product of two odd integers is a perfect square. Let m be the 3 and n be 5. This is two odd integers. Then mn, that is equals to 3, 5. 3 into 5 gives you 15, which is not a perfect square. Then the statement is false with m equals to 3 and equals to 5, serving as a counterexample. Then prove or disprove that if m and n are positive integers which are perfect square, then m plus n is a perfect square. Let m be 4 and n be 9 are perfect squares. So m plus n is 13, which is not a perfect square. So thus the given statement is false with m equals to 4 and n equals to 9 as the counterexample. Prove or disprove that the sum of squares of any four non-zero integers is an even integer. Disprove that the sum of squares of any four non-zero integers in an even integer is an even integer. For any four non-zero integers a, b, c and d, a square plus b square plus c square plus d square is an even integer according to them. Let us take a equals to 1, b equals to 1 and c equals to 1 and d equals to 2. So the a square plus b square plus c square plus d square will become 1 plus 1 plus 1 plus 4, which is equal to 7, which is an odd number. The given statement is false for this, with a equals to 1, b equals to 1, c equals to 1 and d equals to 2, serving as a counter example. This ends this module.